Can you raise the house lights back? No. So if you remember, the little grouping of pictures I just set up here, last time we did, this is the population. If I took, I can't remember now, I think it was 5. I said it should end up like that roughly. Because the most likely thing to happen would take a bunch of young people and old people. Now if you weren't here last time, you might remember the Florida population we did a long time ago about Chevy Chef. Young people, old people. So if I take groups of size 5 randomly, I should be less likely to get a bunch of young people. Should be more likely to get a mixture. So that's why it's going to end up with a big peak in the middle. Whereas this guy had nobody in the middle. If I take 50, it actually will end up being, roughly like that. Because then it becomes really unlikely to be very far away from the middle. You still will have a chance to get 51-year-olds, right? Just choose randomly. I'll choose you. Okay, I'll choose you. Okay, you're all young. So their chance should be down there, but most of them should be right in there, pretty close to the actual mean. Now that, in a way, that hopefully just makes sense. This is exactly what happens, and what's cool is the new mean is the same as the old mean. Of course. I don't care if I take each one of you one at a time, or I take groups of 5 of you and take the average. Average those up, it should be the average age in the room. It shouldn't matter if I do it one at a time or groups. So the mean stays the same, but the standard deviation, of course, shrinks by exactly this much. So all of this is kind of captured in something called the central limit theorem. Basically what it says is, when the larger n gets, the larger the samples I'm collecting, the more normal the distribution of sample means should get. So the larger n gets, the more normal what's called the sampling distribution gets. And let's make that a little more specific. There's so many very vague things in statistics because, again, statistics is crazy honest. We say exactly what has happened, and stat says, I don't know, somewhere around here. But that's honest. That's how life is. The larger n gets, the more normal sampling distribution gets. And this phrase, sampling distribution, this is just the picture that we make when I take a sample. I say, what's your average age? I plot it. So this one was made by, what's your age? Bang. What's your age? Bang. I plotted. This is individuals. That's who this works for. These are for groups of people. That's what this works for. Just change it. I can be a little more specific. If n is greater than 30, we consider it to be, you'll love this, normal enough. Normal enough for what, do you think? Normal enough to sit next to on the bus?
Make it normal.
Normal enough to do what? What's really nice if I know I have a normal distribution and I have questions that I want to answer? Symmetric, I like it, but what do we have? What tool can I use that was not too long ago introduced if I know it's normally distributed? Z-scores to find probabilities. I love it. If it's normal, I could use Z-scores to directly find any probability I want to. If it's not normal, I can't do that. At least not in Stats 1, which is what you're in. Not easily. Let me say it like that. So the larger n gets, the more bell-shaped, the more normal the new distribution becomes as they plot everybody's averages. And that's what I'm going to do. I'm going to take all the averages you guys told me, and I'm going to create the histogram and compare what it used to look like and what it looks like now. And hopefully that will look more normal. We'll see. Secondly, it just says these things. Exactly what I said over there. So if I don't tell you it's normal, you can't use the z-score chart. But if I tell you that I take a sample of like 73, what does this theorem say about it then?
It's normal.
It's normal enough. Cool. So then I don't have to tell you it's normal, because if you take a large enough sample, it will be approximately normal. Normal enough to use the chart. How we doing? Okay. I like it. As usual, mostly not reacting at all. Okay. So the last couple days have been just full of freaking concept and theory. And the really, really funny thing is this stuff is really not easy to understand, so don't beat yourself up if you're still not quite there. But the nuts and bolts, it's almost silly how little changes. So I want to show you exactly what changes. And this is what I told you about statistics the very first day. What gets people at is, when do I use which formula, and when do the formulas change, right? You can make a formula sheet, you can do all that stuff, but you still have to know when to use which one. So here's a good example. I like to pick on, I won't pick on Shaquille this time. I'll pick on kindergartners, because they can't hurt me that bad. So let's say we have kindergartners have a mean height. Let's see what makes sense for kindergartners. 3 foot. So we'll say, all right, good. I like it. We'll say, let's make it 40 inches just to make it nice and round. Sickle. And it's known that they have a standard deviation of, let's say, 4 inches. Right, more than adults, because when you're that age, who knows? You could be just growing like crazy, or it could be, I'll grow someday. So what's the difference between these two questions? Find the probability, let me say in English here, probability that a randomly selected kindergarten kid has a height greater than 42 inches. With me so far? So in symbols, that would be the probability that a single kid is taller than 42 inches, right? That should look very familiar. We should know how to tackle that. And that is not it's a classic z-score problem. The trigger that tells me when this stuff happens is when I take a sample. Right? So if I took, here I'm only asking about a kid, an individual kid. That's what this is made for. That's where that comes from. That's the standard deviation for individual kids. So if I say, find the probability that 38 kids have an average height, have a mean height greater than 42. So in symbols, that would look like this. X bar greater than 42. You with me? What I'm really trying to show you here is, because one of the hardest problems in all of mathematics actually is, I know that, I know how to do that, but when do I do that, right? So in statistics, it becomes actually a little more well-defined. It doesn't become easier. It's just that I have a very defined thing I have to do sometimes. It's just like, when the hell is that? So you do the normal way if I'm taking one thing, individuals. And what do I mean normal way? Of course, normal is probably a bad word to use in general. That sheet we did last time with the ton of normal probability problems, right? We did that last time. Z-scores, and then you had to change it to parking at gross mark, that kind of thing.
Yeah.
This one, when you take a sample of things, then you know you have to first apply this. So let's see what happens, nuts and bolts. How do I do number one here? Let me do the work over here so I get more room. What's probably true about their heights that I haven't said yet? Yeah, it's normally distributed. Which part of this problem would I not have to say that?
Second part.
Second part. But the first part I have to say it's normal. Because I only got one kid, not a big enough sample. So for the first part, what goes right in the middle?
40.
40. What am I interested in?
Finding 42.
Yeah, above 42. So here's 42. So the area is going to be up there. I want this to become very second nature, because we're going to take this process and tweak it in several different ways. This is the first tweak. Right, the central limit theorem is the first tweak. What do I do with that?
You have to find the z-score.
Yeah, make a z-score so I can use the z-score chart. So the z-score, good, 42 minus 40, divided by 4.
0.55.
Yeah, 0.5, I like it. So 0.50. So you'll look up 0.50 in your z-score chart. Oh, I got some of these still.
It would be 1 minus 6.
Good, so if I see this, 0.50 is 0.6915. Where does that go in the picture?
That way.
I like it. 0.6915, so this one's got to be
1 minus
minus that 0.3085. How are we doing so far? That's exactly like the problems we did with the Grossmont people parking, and it was probably they take several years and stuff to park and so forth, right? Thankfully, that would be a very small chance. So what about the second one? The minute I see two things. The minute I see a sample is being taken and they're asking a question about the sample mean. You with me? When I see a sample being taken, do something other than Roman numerals. Sample taken. Question about sample mean. Those two things tell me I have to apply the CLT, the central limit theorem. Right? Which means that the mean stays the same. That's cool. The mean stays the same. But the standard deviation I want to use now becomes
the
what?
new standard deviation.
Yes, the old one. So how do I build this up?
That would be the old standard deviation.
Good. 4 divided by square root of
38.
38, because I'm taking 38 kids. Right? How are we doing?
0.6489.
Good. So how far do you think you have to take this out?
3 decimals.
Yeah.
0.649.
649?
I rounded off.
Does that sound right? I've given all my calculators away, so I don't know.
You still got the calculator on the computer.
I do, but it's way over there. I'm lazy. So I really want you to understand. This just tells me when to do this. The rest of the work, exactly the freaking same. The only difference is going to be instead of 4 here, I'm going to have 0.649, because I can't use 4. 4 is for individual kids. I have to use a standard deviation that works for 38 kids, and that's this. Right? Should it be, I can find a tall-ass kid randomly, and that's not going to freak me out, right? If I just pick somebody randomly, whoa. But if I went and took 38 kindergarten kids, and they're all freaking tall as hell, I'm starting to wonder, where the hell am I? What's in the water? What is happening? You guys kind of with me? So it should be much less likely that I'm far away from the mean. And what measures average distance from the mean? Standard deviation. So the standard deviation gets smaller, telling me, oh, things are not as far away from the mean as they used to be. Groups of 38 should be closer to the mean. So now when I do this work, same picture really. Should be skinnier, but who cares? It's just something for me to kind of have a visual of what's going on. So when you make the z-score now, 42 divided minus 40 divided by 0.649.
3.082.
3.08.
Yep.
So it used to be half a step away. Now I'm 3 steps away. And let's see what that means probability-wise. Look up 3.08. What probability do you get?
It's higher than 0.99999 something.
Yeah, it comes out to be exactly 0.999.
To
So this is 0.999. So this would be
the 001.
001. I like it. So 0.1% chance. For an individual kid, there was a 31% chance almost for them to be more than 42 inches tall. But for a group of 38 kids, for their average to be more than 42 is a very small chance. And that really only makes sense if you think about it. This is just making it much more specific, formalizing what we already kind of know. So this is a 0.1% chance. Maybe. Okay, so like if you went and picked a random Grossman student, if you get somebody who's a perfect 4.0 student, all right, that won't freak you out too much. But if you take 80 Grossman students and they have an average of 4.0, that is a rig. That's not going to happen nearly as often, right? In fact, it's almost going to be impossible. Just because it's such a large sample, there should be some variation in there, right? Okay. Maybe. Okay. Cool. So that's 6.5. The 6.4 is the weird one. 6.4 is related to that colorful handout I gave you the other day. 6.5 involves this tweak. That is the only new thing in 6.5 versus 6.2 and 6.3. Okay, maybe. So what I really want to focus on today is 6.6, and that'll be enough. We'll do 6.7 later. I'm going to run out of time. Maybe I should let me let you guys try one problem out on your own. This is 285. Let's do number 12. So up here, number 12. Effective diet on length of pregnancy. If you can't see that very well, then get a book. Bring your book. See somebody near you? Oh.
So the mean is given and the standard upholds and deviation is given.
Good.
And they ask us if one person
I got one. So that's even better than calling it old. I'll just sometimes call it old, but it's the one for individuals.
Yeah.
So part A needs that one. Good. So which one? Oh. Yeah, I have a couple.
Yeah.
Where did I find that? Who said that? Who wants that?
I do.
I haven't even finished any of it.
So let's see, what's this say here? I'm telling you that it's normal. Yes, sir.
So is it, we use this z-score to find the probability, like got 0.2981. Is it the 1
Yep.
What is
Find the probability. Good. So make a z-score, look it up, get the area. I like it.
So that's it. That's.
Yep. So to draw this picture out, we'll go right in the middle.
The mean.
The mean, 268. And I'm curious about less than 260.
So it's negative.
So 260 down there. Shade that in. I want less than 260. Sorry, I know that the probability is going to be...
Negative.
No, probability can't be negative. Z-score will be negative, but the probability will be less than half.
Half.
Right?
Yeah.
I was interested in it, less than 100%. Way out on the limb. But yeah, it's definitely going to be less than half, and that's just a quick visual. If you get an answer 0.89, you might have forgotten to subtract, or you might have looked on the wrong side of the z-score chart, right? The visual is just trying to help you make sure that your answer makes sense. What do I have to do next in that area?
Z-score.
Good. So convert that to a z-score.
260 minus 268 divided by 15.
And of course, why am I not changing anything?
It's a normal single person.
Single person. And that's exactly what this is for. It's for individuals. Don't have to change anything. Exactly the same deviation I want. So what do you get there?
Negative 0.533.
Negative 0.53? Cool. So to find that area, you just have to
0.29881 is
Just go to a C-score.
that way.
go to the z-score chart, look it up, and you get 0.298?
2981.
2981? So almost 30% chance that a pregnancy would last less than 260 days for any selected female. Okay. Oh, do. If you watch Junior, maybe Arnold Schwarzenegger. So this one, what's immediately got to change first before I do any work,
Standard
really?
deviation.
Good. Standard deviation will now be
The new standard deviation.
Standard
Good.
deviation.
The old one?
Divided by the
Square
square
root
root
of
of
the
And they give me a nice number.
3.
Good. 15 divided by 5 is 3. So I still have basically the same picture. But the z-score will now be 260 minus 268 divided by
3. Negative 2.67.
negative 2.67. Sounds good. So now that would be much further away from the middle, because most of the data should get really close to the middle. When you look up negative 2.67, what do you get for that area there?
0.0038.
Second?
0.0038.
So like a 0.38% chance, whereas this was a 29.8% chance. So now listen, this is if you're trying to check a theory, so the theory here would be, and they don't really say this until you get to that part C. The theory here might be if I change the diet of pregnant women, they put on a special diet, and they want to see if it's going to affect their pregnancy. In this case, maybe they'll say, okay, I got a special diet that'll make the pregnancy less. And hopefully at the same time the baby won't freak out. Right? That'd be nice. The woman's like, I don't want to carry the baby so long. Okay, good. Use a special diet. Your kid's all right. For any women, the probability that, for any group of 25 women, it's almost impossible for the average length to be less than 260. Guys, with me? It's basically what we just figured out. 0.38% chance. So if this person gives 25 randomly selected women pregnant, he gives them the special diet, and they do end up having less than 260 days of pregnancy. What is that probably evidence of? Did he just randomly select women who are going to have less length pregnancy anyway? Or maybe his special diet actually had an effect. You guys start to see, and this is how you use statistics to check something. And in a normal situation, it is so unlikely for that to happen that if I do something strange and I notice this happening, the strange thing I did must have had an effect. In this case, it was changing the diet. It might be giving people some kind of medication, right? You guys kind of with me here? It might be SAT prep class, and you claim that it helps people increase their grades. So if you take a sample of 30 people and you find they get such a high grade that it's such a low probability that it just happened to be that way, you're like, that's evidence. They can say clinically tested. And that's what they mean when they say clinically tested. They just prove that it's very unlikely that it just randomly happened. It must be the medication or it must be the study class. Yeah.
What percentage would be likely?
Good. What do we have so far for unusual percentage-wise? Who remembers? Anything less than 5% would be unusual. That is damn unusual. When we get to chapter 8, we're going to definitely make that a lot more specific, because 5% is a little too general. In some situations, I want to call 1% unusual, or I want to call 10% unusual. I want to be able to change that. For right now, it's 5% because that's what's used most often. Hopeful. Okay. So part C, it says if they blah blah blah. It doesn't appear that the diet has an effect on the length of pregnancy. Should the medical supervisors be concerned? I don't know. But does it have an effect on the pregnancy? Yes. This is evidence it does. What's the probability that I'm wrong? If I say yes, it has an effect. The probability that I'm wrong is 0.38%. That's much smaller than my normal probability of being wrong. That's awesome for me, my probability of being wrong. You see what I'm saying? So if you say the diet has an effect, this chance that you are wrong. So I am pretty confident that the damn diet had an effect, right? Especially if you did it again and it had an effect like this. I'm like, well, that's like crazy evidence. That's why in science you always wanted to replicate. If it happens once, it might have been a fluke. Okay, maybe.
So some people then believe that they fixed the results to get what they wanted to have happen.
That's true.
Or they just say it's a fluke, so it's like,
Yeah.
don't pay attention to
In
it.
every field, you have people that just don't go by the right rules in that field. That's unfortunate.
First, because the scientific method is flawed.
No!
No, it actually is.
Oh, you and I can discuss that later.
I don't get like this.
Okay, so now I want to focus on 6.6 for the rest of class, and I'm hoping we'll see what happens, if I can let us out of here early. Before I do anything, before any of you guys escape, let me give you this practice test. All right. What's happening a week from today?
Test.
Yeah, so you guys should get practice. Pretty good.
No.
I am. I understand all.
Jim, what's up?
I don't understand how it has an effect though. Like they want women to have less than because it says it's a 0.3%.
You're wrong.
Oh.
Yeah, I erased.
No.
You said it was a point. You said it was a chance of being wrong.
Exactly.
Is it because it's going that way? It's wrong?
No. So, in general, and this is not true for all statistical tests, but normally you'll do assume that everything is the way that it should be. So like the last problem we did, we calculated a probability based on what the known average length of pregnancy is. That's assuming everything is the way it should be. It should normally look like that. That actually is what the word normal comes from in statistics. So we found that to have 25 women who had such a short length of pregnancy, if everything else is normal, and just to randomly find 25 women who had that short length of pregnancy, that would be crazy unusual. 0.38% chance of that happening randomly. So, or what could be happening? The diet they ate affected. So what's more likely? We randomly selected women that would have that short pregnancy. That's a 0.38% chance of that. Or the diet had an effect on them. I'd say it's more likely the diet had an effect, right? You with me? So, but if I found that it was only a 25% chance, well, that's not a very small percent chance, to tell you honestly. It's a 1 out of 4 chance. It's a pretty damn good chance, right? That would not be evidence that the diet had an effect. It's not unusual to find that 25 women did that if I found 25%. But we found 0.38%. Just a small percentage that would just happen on its own, that it must have been the diet that made it happen. How we doing? Sort of, okay, good. All right. Okay, so do you guys remember this?
Yes.
Yes. I like to get a lot of use out of my stuff. You guys remember this question? The probability at most 6 heads. And to get that, we had to do what?
Add up what's
Add them up. Add what up?
6, all 6 of the...
Yeah, so I try to give you an example because at least at most people often go the wrong way. But at least would be you have to at least this tall to ride the ride.
Yeah.
So if you're shorter, you're bad. You have to be that tall or more. At most is you can have at most 6 people in an elevator, or you'll plummet, or the devil might come in there and look like a woman.
Good movie reference.
I know. So, somebody help me out real quick. If you add up the first 6 probabilities here, I can't remember what we got. I can't remember if we did that. So at most 6, 7, 9,
395?
395?
0.395.
Yeah. All right. How we doing? Now, doesn't this thing look normal?
Yes.
Shouldn't I be able then to make a z-score out of 6 and just look it up in the chart and not do all this adding of probabilities?
Yeah.
Did you? Yeah. But no, it's good. It's perfect. I sort of led you, but it looks normal. Now we haven't talked yet about why. How do I know if it's normal enough when it's like this, right? I know it's normal enough when I'm picking people samples and it's more than 30. But what if I have a binomial situation, which is what led to this? What makes it normal enough? Well, this looks pretty damn normal. If you drew this histogram yourself, you say, well, that's damn normal, right? Okay. This is obvious, but there's a point where it's like, is that normal? So we're going to talk about that in a minute. But let's assume that is normal. Can you guys see a problem, though? If I change 6 into a z-score and look it up, what is wrong? I'm not quite getting what I want to get. Visually, can you see that? If I take 6 and make it into a z-score and look it up, am I going to get the right area?
Not really.
What am I leaving out?
The height, a couple of heights above. Like,
Yeah, I don't want 6 and below, do I? What's this whole block represent from
6.5.
0,
5.5 up to?
6.5.
So I really should do 6.5 and change that to a z-score, right? Wouldn't that capture the side of the rectangle? Do you guys see what I'm saying? And the problem, the reason that this binomial is freaky is because heights and stuff like that and length of pregnancy, they are continuous, right? I can have a length of pregnancy of, well, not me, but it could be a length of pregnancy of 259.899429 days, right? But if you flip a coin and you get 6.39 heads, what? What happened to your coin on the last flip? It's a little freaky. We'll count that as 0.39. So, what I'm trying to get you to understand, this is our next tweak. We have the central limit theorem when we have to change the standard deviation. Now we have, if I want to use a normal distribution for the binomial, and the binomial is discrete data. I can have 1, 2, 3 heads. I'll always have to adjust the number I'm given up or down by a half to capture that side of the rectangle. Are you with me? Does that sort of make sense? I mean, most of you guys understood what I was trying to say earlier. If I go from 6 down, I'm not going to be... Let's do it. Let's do it. What do I know? What's the mean? We did this one last time. You have your the thing somewhere? We count the mean to be 7, right? So it's 7. That makes sense. It's right in the middle. Mean is 7. Standard deviation was
3.5.
3.5? No.
1.87.
1.871? Okay. So let's try this out. We know what the right exact answer is. We know it's 0.395. That's the exact right answer. So if I take 6 and make it into a z-score, let's see what I get. How do I make 6 into a z-score?
you subtract 6 minus 7.
6 minus 7
deviation.
divided by?
Standard deviation.
Good? How are you doing over here? Okay, good. And what do you get there?
Negative.
Negative 0.534? 534?
Negative 5.3. Negative 0.5.
Is that good?
Yeah.
All right, thank you. So look up negative 0.53. What area do you get?
Like 2981.
That's the exact same z-score we had earlier, I think, on another problem. All right, good. Freaked me out for a second. 2981, is that very close to 395?
Not really.
29% roughly versus, well, 30% versus 40%.
10%.
If your doctor said you have a 40% chance of living, I like 40% more than 30. They're both kind of bad, but I like 40% chance better than 30, right? If you would have said you have a 0.297, 0.298, who cares, doc? Shit. But this is 30 versus 40, that's huge. So that sucks. Something's wrong here. I didn't get anywhere near enough. And you can say it's because I'm trying to use a continuous curve when it's really boxes, right? But the real problem is, the way to make this approximation better is to not make a z-score out of 6, but to make a z-score, like you said, out of 6.5. Why exactly would I make it out of 6.5? Do I want to include 6?
Yeah.
Yes. If I didn't want to include 6, I would just start here and go down. So it's always one side of the bar or the other. So what happens, let's finish this out. What if I instead make a z-score out of 6.5? What do you get? Negative 0.27? Maybe, does that look good? Everybody else is like, I trust them, keep going. All right. And when you look up negative 0.27, what do you get?
0.3936.
Yeah, so if we look up for 6.5, if we look that up 0.39, what did you say? 36. Now, The earlier one, when we did not change the 6 to 6.5, that was 10% off. That sucked. How close are we now to the real answer?
5.001.
We're different in the third decimal place. It's off by 0.0014. Okay, that's like the doc saying 0.39. No, 1.39. This doc, you don't have to go like that. No, I got back to this feature.
0.014% difference.
Yeah, exactly.
Or difference.
So,
Not percent.
the whole point behind 6.6, there's two things actually. The first thing is this. It's, if I'm trying to use a normal approximation, I'm trying to use a normal approximation for a binomial distribution. Oh my God. So it's what I call the NAB, normal approximation for a binomial. So this is what I call NAB, right? Not MIB. NAB. Normal approximation. If I'm trying to use a normal approximation for a binomial distribution, I have to use this thing, what's called a continuity correction. Why does it make sense that we call this a continuity correction? It's a correction from 6 to 6.5 because a binomial is actually not continuous. So math people actually chose a good name, continuity correction. And what happens to my answer, if I do that, it gets a hell of a lot better.
Yep. Yep.
Right? And it's true in general. It just makes your approximation actually good. And why does it make sense? Geometrically, right? The freaking rectangle, I want to go all the way to the edge of the rectangle. Because they really are boxes. So it's almost too simple of an idea. But people freaked out, I understand. Yeah.
Because between the line between 6 and 7 is 6.5, so
Exactly. Continuity correction. So let's see a nuts and bolts problem to show you really what it would look like to do this. And I'm going to be stupid nice on the test. I'll actually say use the NAB to find the probability. So if I say NAB, you know it's this process, this going up and down by 0.5, whichever way makes sense. So what do I mean by that? Let's say a mean of, let's do it this way, sorry. Let me give you a binomial situation. So let's say probability of success is 0.2. N is 6,000. And I want to know the probability that X is greater than, what, Jeff? 1,150. How are we doing so far? That sounds normal, but what's different, of course? I mean, I know to find the probabilities, I want to know two things. Is it normal? If it's not normal, I can't do shit. So is it normal? And make it into a z-score so I can look up the area, right? So, real quick side note about when I know it's normal. Why is this one normal? Because it looks normal. Well, because what's going to be the highest rectangle? What's going to be the highest rectangle?
in the center.
Where the
Center.
mean is. So the mean was big enough. Stay with me now. The mean was big enough so it had room to go up and then room to come back down. What if the mean was 1? The highest bar would be here. So it'd be, would that be normal?
No.
Hell no. What if the mean was 0.3? It would start way high and come down. So here's the funny thing. What really happens is, in order to make enough room for it to go up and come back down symmetrically, the mean has got to be more than 5. So what does that really boil down to? Here's a test for normality for binomial stuff. NAB. NP has got to be bigger than 5. But let me ask you this too. What's the most heads I could get on this? Or was it heads? Heads. What's the most heads I could get? If I flip it 14 times, the most heads I can get is 14. So what if I had a different situation? I had a weighted coin. It always came up heads. So the most likely thing would be 14. So there's not only do I have to have it this way big enough, I also have to have it this way in the middle. So what really takes care of that is the other side would be NQ must also be bigger than 5. So if NP is bigger than 5 and NQ is bigger than 5, the mean ends up being in the middle enough so there's room to go up and come back down. Obviously, I'm leaving out some details. But that is essentially the overview of what the hell came up to this. It's almost silly how easy it is. So checking it out for this, is this normal enough? What's NP? 0.2 times 6,000? 1,200. And that's one of the tests, but what else is cool about NP? It is the mean. So you got to find it anyway. You got to find the mean anyway, so in the process you can say, oh, that's bigger than 5. So that's the mean. So now I know the mean is 1,200. What else do I have to check? NQ, what's NQ? Yeah, P is 0.2, Q is 0.8. If that's 1,200, this has got to be the rest. 4,800 to make 6,000 total. What's true about that's bigger than 5? That's definitely bigger than 5. Therefore, this situation is normal enough. Now imagine it wanted you to do this using the formula greater than 1150. You'd have to do 1151 plus 6,000 choose 1152, blah, blah, plus 6,000 choose 1153, blah, 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 up to 6,000. Or you can do the opposite. 1 minus 0 up to 1150. Both of those involve thousands of calculations. Screw that. So I'd much rather just make z-scores and look it up. Hell yeah. This is what tells me I can't. So since this is true, I know that I can use the z-score chart. I know it's normal enough. So I got the mean. What else do I need to get before I can do z-scores? Standard deviation. What's the formula for standard deviation? Square root of NPQ. So somebody help me out there.
30.984.
Sounds about right. 30.984. Okay. So now if I draw this picture, what goes right in the middle?
1,200.
Careful. The mean, 1,200. 6,000 would be way up there at the very top. What point am I interested in from the question?
Less than
1150, yeah.
Greater than 10.
And I want to be greater. Now here's what you do. To apply the NAD, what do you put over the 1150? What's actually there? A rectangle, a box. So you put the box there. If you want to be greater than 1150, do you want to include 1150? Do you want to?
No.
No.
It's not less.
Greater than 1150. I don't want to include it. So do I want to start? Do I want to start back here and go up? Or do I want to start up there and go up?
Up there.
Up there. That's all it takes. I know it's going to adjust up or down by 0.5. It's just a question of do I want to include it or not. So I don't want to do this. I want to start at what? What's that? 1150.5. It's always off by half, right? Because the next number up would be 1151. It gets its own box.
Oh.
So the middle will always be half off. I don't know. Of course, this is brand new, so you got to let it sink in. But I'm hoping some of you guys look like you're kind of getting the idea. So here's the funny thing. Once I get my mean, my standard deviation, I'm going to make a z-score, and the only difference between this and the old way is I don't use 1150. I use the corrected one. Yeah, so to make a z-score, I'm going to use 1150.5
Minus the mean.
minus the mean. 1,200
By the standard deviation.
divided by
30.9.
30.984. What's that z-score?
Negative 1.5 or 1.6 basically if you round up.
Negative 1.5. negative 1.6.
60, I guess is
Yeah, it was like
599.
597.
Okay. You guys kind of with me? Sort of? Many of you are looking in this direction. This is good. So if I look up negative 160, I'll get this. What do you get when you look up negative 160? Who's got their z-squared chart going?
0.0548.
Point.
0.548. Oh, wait. Less than.
Yeah, negative 1.60.
Yeah, it's 0.0. I got 0.0.
548.
Yeah.
Okay. So what's the actual answer going to be? Because I want greater than.
You subtract it from.
Good. So the actual answer should be 0.9452. Now, real quick, I do want to hold to my promise to let us out of here early. But I want to show you one thing. To check that work, that's an approximation to a binomial. Stay with me. You guys are all like, what? More shit. But to check this, I could do, stay with me now. I could do binomial CDF. To get this, I could do from 0 up to 1150. You with me? So I want to do, the input for this would be n. N is 6,000.
Can't see.
Oh, shoot. N is 6,000. P is 0.2. And X, I want to go up to 1150, because that's the opposite of greater than 1150 is less than or equal to 1150, right? So I want to go up to 1150. That should equal the, holy crap, what did I just do? I love this thing. Okay, yeah, 6,000, 0.2, 1150. Thinking 0.0545, and we got 0.0548. Then to get this answer, I just do 1 minus. You guys with me? So that was really damn close. It's almost never going to be perfect because this is an approximation. I'm using curvy lines to approximate freaking boxes. Should be amazing it gets that close. Okay, that's plenty. So obviously next time we will do several more of those kind of problems. And I'll have the answer key for that practice test.
So we don't want